Hey everybody, good morning. So today we're going to begin the last chapter, chapter 8, which is on quadratic residues. So in the last couple of chapters, we've been looking at polynomial congruences. And we've seen that sometimes they have solutions, sometimes they don't. We've got a theorem, Lagrange's theorem from chapter 6, or chapter 7, which gave us an upper bound on the number of solutions that a polynomial congruence modulo of prime could have. The degree of the polynomial was the upper bound. But these things can still fail to have solutions. So in this chapter, we start off looking at quadratic equations. And we're investigating when a quadratic equation modulo of prime, when that has solutions or not. And that leads us on, by investigating that, we kind of issued that some things have square roots in modular arithmetic and some things don't. And this whole chapter is an investigation of that and trying to understand that. Okay. So, in order to start that, we're going to first look at a situation that's familiar to you, which is the quadratic equation. So, a return to some basic ideas of quadratic equations. Okay, so this will be back to GCSE level or high school, middle school level, whatever. So your problem is that you want to solve this x squared plus bx plus c is 0. Solve this for x, for real numbers x. And everybody, I hope, knows in their mind, that there's a known formula for the solution of this. Okay? So the solutions are given by this formula, x equals minus b, isn't it? Minus b plus or minus square root b squared minus 4ac over 2a, I believe. Right, it's a couple of little extra. There's a the same that is sort of add on to it twice. Unsaid there, just. A not being 0 for 1, yeah. We need A to be non-zero because we're dividing by it, but if A was 0, then we wouldn't really be looking at a congruence at all. We'd be looking at a much simpler kind of equation. So it wouldn't, to consider it like this would be confusing and misleading if A was in fact 0, yeah. So yeah, we certainly want A to be non-zero. Anything else? Not negative, yeah. So this place here where we're taking the square root, see if we're looking for real solutions, this place where we're taking the square root, we want b squared minus 4ac to be non-negative, so to be greater than equal to 2. And that's so that, i.e. its square root exists. Fair enough. Okay, so everybody remembers actually. We'll recall the derivation of this. I mean, how do you derive this formula? Yeah. So you've got the original the original equation. And well, most straightforward way to do it is to multiply both sides of the equation by 4a, first of all. And we know a is non-zero. And that's what justifies this equivalence here. So this is an if and only if. So the first equation is equivalent to this one. The first equation is true, so is this one. So you can multiply both sides by 4a. But if the second equation is true, so if there is an x that makes this equation true, the first equation is true as well. So you just divide across by 4a. And that's legitimate because a is non-zero. Then you do this completing the square thing. The reason we multiplied by 4a was to convert this first term into a square. This is the square of 2ax. And then what constant? So we're going to square this bracket. Give us 4a squared, x squared. Then here, in order to generate the x term, we'll need a b. Because in squaring this, you get 2 times this times this, so that gives you 4a dx. But then it also gives you b squared. There is no b squared there, so you must subtract the b squared. And the 4ac isn't accounted for yet, so we still need that. Okay. So that's just manipulation. And then you just make x the subject, which you can do by, first of all, putting the stuff over the other side, b squared minus 4ac. And it's here where you say that this is plus or minus the square root of this thing. Here is where we need b squared minus 4ac is non-negative. And what's the conclusion if b squared minus 4ac is negative? Complex solutions, yeah. Or if we were asked for real solutions, we'd have to say there are no real solutions. Because if b squared minus 4ac was negative, at this line, you'd be saying that this real number squared is equal to a negative number. And that's false for every real number. So the logical status of this statement down here would be false for all x. So therefore, the original equation is false for all x. So there'd be no solutions. But provided this is non-negative, we can say this, but otherwise there's no real solutions. And then you just got a few steps just to rearrange this to the form of it. So, as I say, that's all. You've seen that a few years ago. Let's try and do the same thing for quadratic congruences. So can we perform the same analysis for quadratic congruences? Modulo a prime. We've got a sequence of algebraic and arithmetic steps there. Maybe we can do the same thing for quadratic congruences. This time about x squared plus bx plus c being congruent to 0 modulo a prime p. Now, before we had a condition that a was non-zero, because otherwise it wasn't really a quadratic equation. We need a similar condition here. We do want this to be a genuine quadratic expression here. So we want to know that a is non-zero. That's equivalent to p not dividing a. But there's another way we can rephrase that when P is a prime number. Because P does not divide A, you can also phrase that as saying that A and P are co-prime, so don't have any common divisors apart from 1. Another way of saying that is, so these are all equivalent statements of the same thing. In case for prime number, A inverse mod P exists. I'll assume further that we're dealing with an odd prime. So P is a prime strictly bigger than 2. And that's good because that's going to guarantee that 4 is invertible as well. And 2 inverse mod. So because I want to divide, I want to multiply across by 4a, and later on in the formula maybe we'll be dividing by or multiplying by the inverse of 2a. So that's important. So my ax squared plus bx plus c being congruent to 0, this is equivalent to, I can perform the same step. I can say this is equivalent to 4a squared x squared plus 4abx plus 4ac. That's congruent to 0. Now, what justifies this equivalence? What justifies the equivalence is that each statement implies the other. And that's true because 4a is invertible. The inverse of a exists, the inverse of 4 exists, so the inverse of 4 times a exists. This is the product of 4 inverse times a. So if the top equation is true, so is the second. The second is true, so is the first. So this is equivalence because the inverse of 4a exists. Completing the square then can be done in exactly the same way. Minus b squared plus 4ac. Use of the multiplication and addition operations, modulo p, they all work the same way. And there's nothing wrong with this. This is just a kind of algebraic manipulation of that. So this is true if and only if 2ax plus b squared is congruent to b squared minus 4ac. Remember, all of these are always mod p. All of these. So far, so good. So far, we've just followed what we did before. But now, what we kind of want to say is that 2ax plus b is congruent to plus or minus the square root of this. Can you do that? Can you take square roots modulo p? Well, we don't know. I mean, we've never mentioned the notion of taking a square root modulo p up to now. If you don't powers, all right. Your powers is multiplying things together. But we've never, we've never considered the case of taking an element modulo p and asking for its square root. Or how many square roots does it have? Like I'm kind of trying to indicate here, it might have 2 square roots, but
because we've done powers, would we be able to say, well, if the inverse of a power, like we have some base and then an exponent, and if that exponent itself can be written as an inverse of the number, so it'd be like the equivalent of saying a to the 1/4.
Yeah, but what is but that just comes back to the same question. Is there square roots? Is there cube roots? Is there? I don't think it's not just a trick of the notation that will magic them up.
Because it's kind of like when you do modular shape, so it's not like say like there's a number when we square it, that equals.
Yeah.
And it do way around.
Yeah. So like what's really going on here? So yeah, it's just we haven't discovered this. So this step would be justified. So we could say, we could move here and say that 2ax plus b was congruent to u, provided such a u exists, so that u squared is congruent to b squared minus 4ac modulo p. That's what we're asking for. So if such a u, so depending on the value of b squared minus 4ac, if there was an element u, one or more elements u, such that when you squared them, they gave you this value, b squared minus 4ac, then you could say that a solution will be generated by putting 2ax plus b congruent to that, okay, provided such a u exists. And then from there, you could then say, well, that's equivalent to don't deal in fractions, we deal in multiplicative inverses. Okay, so the final formula looks a bit different because you don't have a square root sign, you don't have a fraction, but it's the equivalent thing. Minus b plus the square root divided by 2a. In this case, you say multiplied by the multiplicative inverse of 2a, which we know exists. We know the inverse of this exists because 2 is invertible, a is invertible. So there's this condition in the red box which we haven't really considered much up to now. Does everything have a square root mod p? Do only some of the elements have a square root? P is any prime. Can you name me an element that does have a square root? Consider the simple elements mod p. Well, 1 has a square root. Yeah, because 1 squared is always gives you itself 1. So certainly 1 is a square root. But the questions. Do such u exist? For all elements mod p? Only some. How many square roots? Is it like in the real numbers where if something has a square root, it's got 2, except the special case is 0? Some numbers have a positive square root and a negative square root. Is that the same situation mod p? Could they have more than 2? How do we find it? So just from considering a quadratic congruence, you immediately kind of bump up against this issue, and immediately we have all these questions popping up that we haven't done any theoretical work on. So in the absence of knowing anything theoretical about this yet, what we should do is just look at some examples. Yeah? Look at some initial simple examples. simple p. Simple p means small primes p. So, and we said above that p was an odd prime. So the first prime to consider should be 3. Congruence classes, mod p, there's not too many of them, just 0, 1, and 2. If you're working modulo 3 and you consider the squaring map, so this is the map that takes an element and squares it. Well, you square 0, you get 0. Square 1, you get 1. Square 2, you get 1. Square is 4, which is congruent to 1 mod 3. So, got two things that have square is not a root mod 3. Because everything is congruent to 0, 1, and 2. They square to give you 0 and 1. And 3, okay, there's only 3 isn't that rich an example. 5 is a bit better. Start squaring mod 5. You can see what happens. 0 goes to 0, 1 goes to 1, 2 goes to 4, 3 goes to 4 as well. Yeah, 3 squared is 9, which is congruent to 4 mod 5, and 4 goes to 1. 4 squared is 16, which is congruent to 1. Or another way of saying that is 4 is congruent to minus 1 mod 5, and you square minus 1, you get 1. So 0. Well, 0 is always going to be there, isn't it? 0 squared is always 0. 1 is always going to be there. 4 is there. Of course, we kind of knew 4 was going to be there. Why did we know 4 was going to be there as a square? Congruence class mod 5. 2 squares 4. Yeah, 4 seems a special case there. 4 is a square integer anyway. We should definitely expect it to arise as something that has a square root. 2 is still not a square. 3 is still not a square. Maybe 2 is never a square. Yeah, maybe the only things that come up are things that are square integers anyway. 5 is still a smaller, there's not too much going on mod 5. Go to mod 7. Remember, we're only looking at primes. Zero goes to 0. We should probably stop writing 0 down. It always behaves the same. 1 goes to 1, fair enough. 2 goes to 4. 3 squared is 9. 3 has gone to 2. So my putative conjecture that 2 was never a square is now shown to be false. 2 is sometimes a square. 2 is a square mod 7. 4 is 16, which is 2. So 4 also squares to 2. 5 is 25, which is 4. 6, well, 6 is minus 1. If you square minus 1, you get to 1. And we've got zeros, we always have. We've got 1, we've got 2, we've got 4. 3, 5, and 6 are not squares mod 7. And my conjecture about 2 was mod. Any other conjecture we might start to see there? Any other pattern we might start to see?
It's like,
Right?
every time you have one more number than they.
Yeah, that's true. So we might expect, well, it's a special case here is 5 is 2 bigger than 3, 7 is 2 bigger than 5. The next prime, though, is going to be 11, which is 4 bigger How many things that have square roots might there be in mod 11? What's another way of saying quadratic? So Ali's noticed. So 10. Just because there's going to be 10 things that have, but that's too many because when there was two, I mean, if you get rid of 0, when there was 2 non-zero classes, one of them was a square. When there was 4 non-zero classes, we had 2 as a square. When we had 6 non-zero classes, we had 3 as squares. So it's maybe it's half of the elements.
Do we not include 0?
Well, 0 is always going to be a square of itself, and nothing else squares to 0. 0 is a special, and you have to remember also that what we're doing here is the operation of squaring, which is multiplication. When we looked at the group under multiplication modulo p, remember we had to throw out 0, because 0 doesn't have an inverse. So really, the multiplicative system, 0 doesn't behave that interestingly when you multiply it. So we normally just look at the non-zero things when we're looking multiplicatively. But let's just do an example P11 as well. See that 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And you look at where these all go. Going modulo 11. Doesn't be too easy to do. Okay, 1 goes to 1. 2 goes to 4, of course. And we expect things to go to 9 as well, don't we? We've got 9 now, so 3 is going to go to 9. 4 goes to 16, which is 5. The 5 wasn't a quadratic residue mod 7, but it is mod 11. 5 squared is 25, which goes to 3. 6 squared is 36, which also goes to 3. 7 squared is 49, which goes to 5. 8 squared is 64, which goes to 9 as well. 9 squared is 81. 77 goes to 4. 10 is minus 1, so it's going to be 1 as well. So again, 1, 3, 4, 5, 9.
Kind of symmetry, isn't it? Like 5 and 6 go to the same, 4 and 7.
Yeah, so what symmetry have you seen? What's the symmetry?
So like, if you imagine 6 would be written as minus 5.
Yeah.
7 is minus 4. 8 is minus 3. 9 is minus
5 and 6 are going to the same place. 4 and 7 are going to the same place. 3 and 8 are going to the same place. 2 and 9 to the same place. And 1 and 10 to the same place. You're right, these are negatives. So 6 is the negative of 5 and vice versa. 7 is the negative of 4 and vice versa. So that's right. So again, we see 5 from 10 have square roots. So i.e. half of the non-zero classes, because here it was 3 from 6, here it was 2 from 4, and here it was 1 from 2. Also, what you spotted, and it kind of, once you spot it, it seems obvious. That x and minus x, well, x squared is congruent to minus x squared, modulo anything, basically. So that says if something is here having a square root, it automatically has at least 2. because it'll be itself and it's negative, provided its negative is different. But with odd primes, p and odd prime, x is always different to minus x mod p. P is an odd prime. Remember, p is an even number, then the exact, if n is an even number, then n over 2 will be an integer, and then the negative of n over 2 will be the same congruence class, modulo n. So if something does have a square root, it will have at least 2 of them. And Lagrange's theorem tells us, remember, Lagrange's theorem tells us that a polynomial congruence modulo prime has at most, the degree of the polynomial is an upper bound on the number of solutions. So here we're talking about the polynomial x squared is congruent to one of these. So it's a quadratic polynomial. So Lagrange's theorem tells us it has at most 2 solutions. So we've noticed each congruence class has 0 or 2 square roots. So the facts we've used there is that x squared is always congruent to minus x squared, and x is always different to its negative, and Lagrange's theorem modulo p. Chapter 7. So that's a bit of a discovery. And maybe there's the beginnings there. Maybe that's, you can kind of see how you could do a proof then that always half of the elements of squares and half of them don't. Because they always double up. You know, x and negative x, they're always going to be a doubling up on top of the things that have square roots. So that means, because this is a map from the same set to itself, and if you have this doubling up feature, that means half of the things aren't going to be the image of anything under the map. Yeah. Because if you always have pairs of elements here being mapped to the same element, so it's going to leave half of the elements without anything mapping to it, just by simple counting procedure. 10, which is minus 1, this is not a square root. 6, which is minus 1 mod 7, is not a square root. But then you see 4, which is minus 1 mod 5, it is a square root. 1, which is minus 1, sorry, yeah, and then 2, which is minus 1 mod 3, is a square root. So sometimes minus 1 is not a square root, but there's at least one occasion where it is. So these examples, yeah, and we've also noticed that, of course, if something is a square integer to begin with, namely 1, 4, and 9, of course, it also has a square root in modular arithmetic. Yeah, because it has a square root in the normal integers anyway. 3 squares to 9, 2 squares to 4, 1 squares to 1. And because of this, x squared is congruent to minus x squared, it also picks up a second square root. So I think now we just need the, I mean, we could keep going looking at examples. We would hope to see this, I think, yeah, we proved it more or less, that half of the non-zero things are going to have square roots, half of them won't. That comes about because of the doubling up procedure. We'd always see this, 1, 4, and 9 are always going to have square roots. And when the modulus gets big enough to take in 16 and 25 and 36, they're always going to have square roots because they've got integer square root anyway. But for the other numbers, for the things that aren't obviously squares, 3, 7, 8, sometimes they'll occur as squares, sometimes they won't. So there's a bit of a mystery there. So now, although the term square root is a good, meaningful term, it's not the official terminology that we use, okay? So if we just return to the notes now, on page 54. And so we don't use the term square root. Instead, we use the term quadratic residue. I mean, they're different. We're in a different domain. We're in modular arithmetic as opposed to normal arithmetic. So it's maybe good to have a slightly different term. So this is the definition here. We always have p as an odd prime. We're considering this quadratic congruence mod p, x squared congruent to n, where n is a non-zero congruence class. If this has a solution x, and if it does have one solution, it'll have two solutions, x and it's negative, modulo p. Then we say the n is a quadratic residue. Residue is, the sticky stuff that's left on your fingers after eating your lunch or whatever. Residue is something that's left behind by something. Yeah. So when we say it's a quadratic residue, we mean it's left behind after you do a quadratic operation on something and you divide it by p. It's the remainder after you divide x squared by p. So n is a quadratic residue. It's left behind after dividing by p, after dividing something that you've squared. So being a quadratic residue means having a square root. That's true. That's the way to remember it. So it's not the thing that's squared, it's the thing that has the square root. So being a quadratic residue equals having a square root. Now, in real arithmetic, the things that have square roots are the positive numbers. The negative numbers don't have square roots. Maybe the answer is as simple as that. Maybe the positive numbers mod p have square roots and the negative numbers don't. Maybe that's the simple resolution of this. Maybe it's exactly the same as in arithmetic. So what's the problem with saying that? So in real arithmetic, it's easy to recognize the things that have square roots. They're the positive numbers. The negative numbers, they don't have square roots. Maybe the situation is like that in modular arithmetic too. But what are the positive numbers in modular arithmetic? And when we were looking at our examples here, I mean, mod 10, you've got congruence classes labeled by these things. Everything looks positive. But of course, these are just representatives of the congruence classes modulo 11. Equally well, I could have called these -1, -2, -3, -4. I could have chosen different representatives. Remember, each of these things here is representing an infinite set, a congruence class of integers modulo 11, which contains positive integers within it and negative integers within it. So there's no immediate natural sense of positive things and negative things modulo p. You just have things that you can add and multiply. But there's no initial immediate classification of, oh, these ones are positive and these ones are negative. However, it's through this procedure, this concept now of quadratic residue, this now is identifying for us, well, maybe we should regard 1, 3, 4, 5, and 9. Maybe we should regard them as being the positive things, modulo 11. And 2, 6, 7, 8, 10, the other half, being the negative things, modulo 11. And there's a lot of meaning in that. Okay? So it's, which will develop as we go through the chapter. Okay? So it isn't that, oh, the answer is that the positive things here have square roots and the negative things don't have square roots. It goes the other way around. It's the things that have square roots we shall think of those as the positive things. And the things that don't have square roots, maybe it makes sense to think of them as the negative things. What happens when you multiply together two negative numbers? In the positive negative classification, what happens when you multiply two negatives? Get a positive. -2 times -3 gives you +6. If we were to call these red ones the positives, mod 11, and the black, the non-underlined ones, the negatives, does that work? When you multiply two negative numbers, mod 11, so 10 by 8 is 80, but mod 11, 80 is 3. 3 is a positive thing, or might be called a positive thing, mod 11. Take another example, 2 and 7. 2 and 7 are about negative. You multiply 2 and 7, you get 14, which is 3. You get 3 again. Positive. What happens when you multiply a negative by a positive in normal arithmetic? You get a negative. Yeah, negative by positive gives you negative. You try that here. Say 5 is a positive times 7. 5 times 7 is 35. 2 mod 11. 2 mod 11. 11 doesn't have a square root. 3 by 10 is 30. 30 is congruent to 8 mod 11. 8 doesn't have a square root. So some things, those things start to check out. That's just an observation. Well, we'll make that a lot more concrete soon enough. So that's our initial definition. Example 8.1, well, we've just been doing versions of example 8.1. So we're left with these questions, which I kind of put some of them down there. Firstly, for a given prime, we might be interested in determining which of the congruence classes are quadratic residues, which are non-residues. For a given integer n, we might be interested in determining for which primes p is n a residue, and which primes is it not a residue. Is it a quadratic non-residue? These questions are the kind of questions we want to be able to understand, okay, in this chapter. So I'll be seeing you for a lecture tomorrow. So we'll start to get into this and start to build up the theory about it when I see you tomorrow. Okay, thanks for your attention. I shall see you then.